Few lectures on Gaussian process regression. We have thus far seen the basics of Gaussian process regression, and we have also seen some practical use cases and some code that we've written in GPy. But one of the important questions in all machine learning algorithms is how do we optimize the parameters? So thus far we have not seen how to optimize the set of parameters in Gaussian process. So one of the questions you might have at this point is what are exactly the set of parameters here? Any thoughts on that? So we're going to be making some simplifying assumption while learning the parameters for Gaussian processes. And in terms of the parameters, I'm going to be focusing on the prior that we specify. So prior in the Bayesian sense, where we specify the mean and the covariance function, right? To make things even more simpler, I'll be talking about only a simple specific example of the RBF kernel. Although having said that, our methods are more general, and I'll be also assuming a mean prior of 0. So the only set of parameters that we are going to be learning in this discussion are the kernel function parameters. And broadly, in many of the algorithms, we have seen that finding the optimum set of parameters boils down to just two things. One, writing the expression for the log likelihood of the data in terms of the kernel parameters, in terms of the algorithm parameters. In general, we do that, and then we use gradient descent or any other optimization technique to find the optimum set of parameters in the iterator sets. So essentially, this lecture just boils down to figuring out the log likelihood. So the log likelihood of the data given the set of parameters, right? So we have previously mentioned that we can discuss about Gaussian process regression in the noiseless case as well as in the noisy case. So for the noiseless case, we had said previously that given this data xi comma yi, where we have n train points and star test points, we have this expression where y and y star jointly are a multivariate Gaussian, and we also know from the conditioning rules of Gaussian, we know that what is the posterior of this distribution given the prior. So let's just consider the train data. So the train data is capital N points of the form xi comma yi, and from this multivariate Gaussian, we can apply a conditioning, and we can marginalization, and we can directly write that. So this should have been a marginalization and not a conditioning. We can write that y is distributed normally. It's so subscript n denotes that it's a n-dimensional multivariate Gaussian with a mean mu and covariance matrix k. So mean mu, covariance matrix k, and we have, to simplify matters, we've assumed mu to be 0. So we can make the simplifying assumption because we can always mean center the data, which means we can always center the data to be mean 0, and thus we can apply this assumption. So we then write y is distributed normally with the mean 0 and covariance matrix k. If you remember, for the noisy case, the only difference that we had was that there was associated with each observation a noise term. So the only thing which we need to now vary is that the covariance matrix is the sum of the original covariance matrix plus some a noise term, which is generally written as sigma squared noise times identity matrix. And since we have n points, so this identity matrix is of n cross n. Now, what we need to do is to expand this multivariate Gaussian and then just apply a log over it to get the log likelihood, right? So we essentially, what we wanted is logarithmic of the probability of y given x and theta, where x is the training is the input features, theta is the set of parameters associated with the kernel, and y is our training observations, right? So we just expand this expression y is normally distributed to the mean 0 and covariance of k plus sigma squared noise times the identity matrix. And so this is basically logarithmic of the division of these two terms, with the numerator is exponential of minus half times y minus, it's generally mu, but in this case since mu is set to be 0, y minus 0 transpose times k plus sigma squared noise in inverse times y minus 0, and the denominator is 2 pi raised to power n by 2, and the determinant of k plus sigma squared noise in raised to the power half. So thus we can just simplify this expression and write the log likelihood as minus 1 by 2 y transpose m inverse y, where we're just defining m as k plus sigma square in, and we have a minus half logarithmic of the determinant of this term and minus n by 2 logarithmic of 2 pi, right? So we have now defined the log likelihood of the data, and essentially this was the most crucial step towards understanding how do we estimate the parameters of a Gaussian process. So in this notebook, I'll be using AutoGrad, which some of us have already used in our earlier assignments, for automatically computing the gradient of an objective function. So I've used AutoGrad. I've imported autograd.numpy as np, and on the other libraries, I'll be using gpy also as a reference implementation. So we can always compare our result against the gpy implementation. The first thing, since we're using our own functions and our own gradient descent routines, I'll be defining my own RBF kernel also. The formula is fairly simple: sigma squared times exponential of minus x1 minus x2 the whole square divided by 2l square, where L is the length scale term and sigma is the associated variance. Sigma squared is the associated variance. And I've also now defined a kernel in gpy. It's the same kernel. So if you see, I've defined an RBF kernel. Now what we're going to do is to ensure that our kernel is the same as the RBF kernel. This is just a sanity check. So I've applied our kernel on the input x1 equal to 1, x2 equal to 0, sigma being 1 and L being 1. And I've verified that this is the same as the gpy's RBF kernel applied on the input 1, 0, and the default parameters variance 1 and length scale 1. And this returns the same set of, this returns a true means that the kernels are matching. So that's a good start, that the kernel is matching. And now we'll go to the GP regression, which we have seen before. So we have seen that we had previously created a data set like this. This is a data set of 20 points between 0 and 4.95. And based on this definition, or this result that we've obtained, I'll be writing now a function for the log likelihood of the data. In fact, I'll be writing a function for the negative log likelihood. So in general machine learning literature, we instead of maximizing the log likelihood, we generally do minimization of the negative log likelihood. So that's just a convention often being followed, that we're trying to minimize the objective function. So I've defined the negative log likelihood function here, which takes the parameter sigma, L, and noise standard deviation. So noise standard deviation is defined for the noisy case. So sigma noise is the noise standard deviation. So all I've now done is to obtain the covariance matrix. In this case, this is the matrix M defined above, which is the RBF kernel evaluated over the input X, and then the noise term is added over it. Right? So all I needed to do was to compute this term negative log likelihood, which is half of y transpose dot covariance matrix inverse, so covariance M inverse in this case, dot y, the matrix product of these, and plus the other two terms. One was logarithmic of 2 pi and the other was logarithmic of the magnitude of the covariance matrix, right? And I'll be now comparing the negative log likelihood that we get using our function to the negative log likelihood that we'll get using g pi. So I'll fix a set of parameters and try to ensure that we get the same set of the same output. I have fixed all of the three parameters, sigma, ln, noise standard deviation to be 1, and I get the negative log likelihood to be 40.1. I have done the same thing using gpi. I've set the length scale of the kernel to be 1, the variance of the kernel to be 1. I'm learning a GP regression model on the training input x, y, kernel k, and normalizer equal to false, and I've set the Gaussian noise to be 1, which is the same as the last parameter previously. And I've printed this particular, so I've printed the objective function. So the objective is 40.10, which is matching exactly. So there might be some small deviation, but that might just be because of some floating point calculations. And this is just to verify that the regression has the same set of parameters at which we get set. Right. So one small caveat here is that I've set the normalizer to be equal to false. What this does is to ensure that we are not mean centering the data. So we are not we're not making y to be normally centered with mean 0. So that's an important caveat to be aware of. And now, as we've done previously in the previous lecture, we saw that we can optimize the GP using gpi. Optimizing GP means to figure out the optimum set of parameters which will minimize the negative log likelihood or maximize the likelihood, right? So I've just done that. I see that the objective is minus 2.94. The variance is 27.8, pretty high. The length scale is 2.7, again pretty high. And the Gaussian noise variance is pretty low. So one of the reasons why Gaussian noise variance is pretty low is that when we had originally defined or created this data set, you notice that the random noise that we had added was pretty small. If this was bigger, then we would have obtained the optimum noise variance parameter to be slightly bigger. Right? So once we have done this, now we're going to be trying to see whether the negative log likelihood function that we have, if we evaluate over the entire search space, are we able to get closer to the optimum set of parameters and the optimum objective, right? So this is something we've been doing before. We are now going to plot the negative log likelihood as a function of the set of parameters. But we have three parameters: variance, length scale, and the Gaussian noise, right, in the noisy case. But what I'll do to make things simpler is to use this value of Gaussian noise variance, which is the optimum value from the learned using gpi, and I'll be looking at the search space over the variance and the length scale. So in this particular piece of code, I have set the Gaussian standard deviation to be the square root of what is obtained over here, and I've tried to find the negative log likelihood over the entire search space defined on 0.126 with gaps of 0.04 and 0.124 with gaps of 0.03. And this is how the contour looks like. So remember, we were trying to minimize the negative log likelihood. So this is the region where we'll want to learn some parameters on. So the x-axis is showing sigma, the y-axis is showing length scale parameter L. So it seems like there is not just one parameter, but a range of parameters which seem to be giving us fairly similar amount of negative log likelihood. And just to verify the set of parameters that we've got, so in this 2D matrix, I was storing the negative log likelihood for each point in this grid space. And I'm showing that the minimum value that I'm learning is minus 2.94. And using gpi also we had obtained something like minus 2.94. So this seems to be fairly good and fairly consistent. The optimum set of parameters which give this minus 2.94 seem to be 28.09 as the variance. So if you see, I've done the square here, and the length scale to be 0.1. This is not exactly what GPy is returning, but not very far. And as we can look in the contour plot, there seem to be a lot of values where we'll be getting fairly similar log likelihoods. So not a huge cause of concern given that the objective is fairly similar, which also tells us that there'll be a lot of local optima. So which means that an optimum way, a good way of finding the best set of parameters could be to start to have multiple different random initializations. So this is called multiple restarts. And then finally choose the set of parameters where the overall objective is learned to be the lowest. Right? So what we've thus far done is to visually try and inspect and see what is the optimum set of values we can learn for the different parameters of the Gaussian process. But we have been looking at a much better way of doing the same, which is using gradient descent. So all I've done is to define a function which returns the gradient piece. So it returns an element wise. It returns me the gradient with respect to each of the three parameters: the variance, the length scale, and the noise term. That's defined in this function. So it's a gradient grad over the function and over the three arguments. And all I've now done is to just apply to find out the gradient with respect to each of the three parameters. Del sigma, del L, and del noise are the gradients with respect to three parameters, and just use vanilla gradient descent update rules to optimize the set of parameters, and then for every iteration I've computed the negative log likelihood for the updated set of parameters. And in this plot I'm showing the optimum, I'm showing the negative log likelihood as a function of the iteration. We can see that initially there is a lot of very steep drop. After that there seems to be some amount of oscillation. So this could pretty much be corrected using a learning rate which decays over time, right? So that would get rid of this oscillation kind of behavior. But anyhow, that's not the focus of this particular discussion. And what I finally want to show is that I've started off with some parameters, sigma 2, L2, noise 1, and I've applied the same gradient descent procedure, but I've not stopped here. I've also now tried to plot the fit, right? So to make things simple for me, I'm just using GPy for doing the plotting for me. The only thing I'm doing here is that for the kernel parameters, I'm setting the length scale to be L, which is updated after each iteration in the gradient descent procedure, and the variance also. Similarly, the Gaussian noise. So the Gaussian noise, variance, and length scale are being fed in the values which we are updating using the gradient descent procedure. Everything else remains the same, and I'm just making a plot using GPy. I'm saving the same for every iteration, and then I'm combining this using a simple Unix utility called convert to a GIF. And in this GIF, if you can see that as we increase the number of iterations, one, the objective becomes fairly good. It reduces to a very small number, and then it shows some amount of oscillations. Now we again starting with iteration 0. So you can see that initially our parameters were really bad. There was a lot of Gaussian noise assumed about each point, which in the optimum set of parameters is reduced. And of course, if you see that there seems to be high amount of variance between -1 and 0 and 5 and 6, that is expected because there are no train points in that region. So, and if we were to extrapolate this further on the x-axis, on either end of the x-axis, we'd see that these points would eventually be going close to, so the predictions would be going close to mean zero, because that's what GP would do, because that's the pri that we have specified. So this was a short and crisp lecture on how to learn the optimum set of parameters. This is not the only way to learn the set of parameters. There's other Bayesian ways of doing the same, but we are not going to discuss that for now. And I also wanted to suggest a couple of quick things that you might want to try out based on this. One is gradient descent procedure with restarts. As we discussed before, because since the optimization surface will have a lot of local optima, you can, so it might be good to start off from have multiple start points, random start points, and then finally choose the start point, finally choose the set of parameters which give the overall optimum objective. The second thing is that I mentioned that we have assumed mean zero, which we are not asset following because we've not mean centered the data. So that's a very simple to-do that you might want to have after this, to mean center the data and then apply the same set of rules. In GPy, you can just use the default parameters or just set the normalizer equal to true and you should get the same effect.